All right, good afternoon, everyone. Happy Friday. So it's my great pleasure to introduce our distinguished speaker today, Professor Junbo Zhao from University of Connecticut. I think there's a long list of titles here, as you can see how distinguished his career is. Right, he has been a director for multiple DOE-funded projects, a research scientist of Phineas National Renewable Energy Lab, and also a junior chair professor in the ECE department in Connecticut. I would say really Professor Zhao is one of the emerging leaders in the area of energy and power systems, particularly well known, recognized for his work using AI for a variety of power systems problems across scales. I'm sure he's going to give a very fantastic talk here. Without using too much of time, let's welcome him to Cornell, please.
First of all, thanks a lot, Fonchi, for your kind invitation. Actually, to be honest, this is the first time I visited the campus, although I know a couple of colleagues from Cornell. But I'm so glad to be here, and you guys are so warm, kind for my visit. So for today, I'd like to share some of the works we have been doing the past few years, including one. Actually for today, I kind of formed the problem into a setup where even you don't have too much background in power system, you should be able to digest which type of problems we're addressing, so that it may give you some of the ideas. There are certainly some technologies that can be quite broad to other problems, but in general, for today's talk, we're going to think about how we're going to merge the data with the physical information. AI for this year has been given to a couple of Nobel Prizes there, right? It's so popular. But we are dealing with a power energy system. It's quite safety constrained. We have to make sure all those AI technologies, they should follow the physical laws. That's where it came to our mind, how those model and data, they can work together to give you better performance, or it can give you the power to address some problem which you cannot address in the past. So that's something I'm going to talk about today. But to begin with, I'd like to share a couple of major initiatives we are doing, and those are quite broad, at least in our domain. I'm just leading a team to do some of the works, but it's quite broad, especially for some of you guys who are working in power energy. I would like to give you some of the major initiatives we are doing, and then I will dive into the problems. Specifically, we are addressing the problems relevant to our today's talk, especially in physics-informed learning and analytics for power energy system optimization and control. So to begin with, I'd like to share a little bit more about these initiatives I'm currently leading, which we call CyberCare. It's the DOE Northeast Cybersecurity Center. And for this one, we are working with a couple of universities across our region, together with local governments, to build really the curriculums, as well as unifying the technologies in our region to talk about the cybersecurity for energy systems. And this is unfortunately currently lacking. We see strong needs from both the university workforce development as well as for the power industry. They don't have the knowledge to handle the digitalization of the power grid or power energy systems. So we're working with 20 plus industry members together, just to make sure our developments as well as the curriculums, they are aligned better with what the industry is looking for. So that's really the purpose. And for this initiative, you see we have 5 major pillars. The first one is that we need to understand better what could be the cyber attacks that can happen in reality, right? So we have to capture this. So for this, we're going to work extensively with industry members to better understand from the computer networks or cybersecurity perspective what could be the scenarios in power energy systems. And then we're going to put those emulated scenarios into our hardware-in-loop simulation platform so that you can, at least from the digital twin perspective, you can understand what could be the potential impact to the grid. And then from that, you can analyze and get some of the vulnerability assessment or risk scores for the critical infrastructure. And with those understanding, it can give you a better ideas how we're going to develop some defense modeling approaches, right? How we are going to detect them, localize them, isolate them, or mitigate their impacts. But not the last, but not the least is really the education and engagement. So for that, we want to make sure our developments, our curriculums, they are available to the power industry and all the communities. So we are going to build some of the website, which will be quite widely accessible to other folks. So this is one major initiative we're currently doing for the Cyber Security Center, DOE Center. The other one is really more complicated. We're trying to merge together with the climate change, together with the power energy infrastructure, and also with human in the loop, which is related to the communities. So for that, what we are doing that, nowadays we are seeing a lot of extreme weather events. The problem we are thinking that for a given like weather forecasting, can you forecast how the critical infrastructure are going to be affected? So for that, we're going to develop a really granular outage predicting systems for the distribution circuits. For example, for tomorrow, you are going to have a big, snowstorm or hurricane events. Then we're going to tell you, for this county or for this circuits, how likely or how many customers they are likely going to get outages. And from there, you can inform the stakeholders or communities, okay, I need to put some certain critical needs for the community, or how we are going to dispatch the crew members for faster restoration. So this is one major piece of work. It has been there under Eversource Science Center for many years, but we are pushing to the next level, from the county level to the circuit level, which will be really, really relevant to the communities and for the local governments. And then on the other hand, we are going to install more grid edge intelligence sensors. For example, the grid matrix data, they are coming from communication companies. For example, those cable companies, if you drive through the road, you'll see, there are power lines, three phases. There are also, in parallel, there are some of the cables in parallel with the power lines. Those cables, they are powered by the electric poles. And at some certain aggregation points, they have measurements. For example, the voltage and frequency measurements. And the voltage measurements, they are so helpful for power distribution analysis. And this is out of the band, meaning that utilities, they don't have any information, but this is owned by the communication companies. So our innovation is that, can we bring those information together with the utility information to have a new systems? And for those sensors, they are through the, fiber optics. There's almost no delay, and they can be updating very fast, much better than the AMI meters. So we're going to have those installed communication, out of band cable company data together with some more advanced like grid edge, like powered by Inveda for the smart meters. They can have certain local intelligence so that we can better diagnose what's going on from the grid edge perspective, or detecting any outages that are not forecasted by the outage prediction systems. With all those visibility and feedback into the grid restoration process, you can rely on the DER control microgrid solutions to help accelerate the restoration. So this is another major initiative we are doing, and this is the second year of the project. We're going to do our actual implementation in one of the communities in state of Connecticut. The third one, which has been pushed so greatly this year from the FERC level, Congress level, even at the state and local governments level, is that how we're going to better utilize the capacity of existing transmission assets or transmission lines. The technologies the industry are pushing is related to the dynamic rating as well as advanced power flow controls. So for this project, we're working with local utilities like Eversource in the New England areas. We're going to install dynamic and lighting sensors along this transmission line to better understand the big offshore wind integration into the grid, whether you can really utilize the transmission capacity without investing new transmission lines. Because for new transmission lines, very time consuming, it has regulatory challenges, and also there might be against from the communities. So a better way of better utilize the infrastructure is to measure what is going on real time and then feedback that information to the advanced controllers. So we are going to collect more information through these initiatives. Actually, this project just gets started, but we're excited to get the first experiences in our region, especially for the offshore wind. We are the first in the country to study the impact from the offshore wind impacts to the transmission lines in the field, which I'm very excited. And for more information, I think we recently have an article on Nature Review in Clean Technology. It just accepted, so you can have more information from what is grid enhancing technologies, what is the development across the world. We have a lot of data and stories across the world. You can take a look at. So at least those are the three examples our group have been pushing. And also this is really at the frontier of the industry. I would like to share with you guys before I'm diving into the today's topic. For today's topic, really the first challenge we want to address is, again, look at the renewable energy integration, right? So it's going to be accelerated so much. While integration is such a high potential renewable energies, you have to handle a couple of challenges. First of all, those are power electronics-based devices. They likely do not have any inertia. Very different from the synchronous generator, you have lots of inertias. And that gives you fast dynamics. And also, those are weather dependent. They may have some huge uncertainties, right? How are you going to manage those uncertainties? So this is the one first big challenges. And one particular event related to that is the 2016 South Australia blackout. Because for that particular system here, it has very high penetration of renewable energies. And due to that lack of inertia, you see the rate of change of frequency mean that frequency is changing too fast. And the protections and some of those controls, they are not designed for handling such a fast dynamics. And at that point, that gives us a lesson. First of all, you need to plan or do preventive type of controls in a very fast manner, or emergency controls. So for our groups, we work a lot on the preventive control, before that event's happening 50 minutes ago, what type of actions you can do to prevent this type of events, or later on the emergency control. But this is another topic which we're going to work on. From the inverter-based resources perspective, at least some of the major events happened in the past few years. For example, this is a report from the NERC report. It captures the real events. You see the disturbances in the grid. They can cause cascaded outages for the big distributed energy resources like solar farms. You see solar PV resources. Some of the batteries, they may be tripped, or even some of the oscillations between the inverter-based resources to the natural gas facilities, and they are causing certain very complicated interactions. We have to better understand that and design some operational mechanisms to prevent this type of impact to our grid. The other thing that with the IBRs mean that we're not always criticizing, inverter-based resources that are not good, but actually in the meanwhile, since they are power electronics devices, they can, if you do it right, they can provide a lot of services. Like you can provide through the controls, you provide some inertias, you can provide frequency support, you can provide voltage support, and so on, right? Those are good things. You can take advantage of it. But from the optimization and control perspective, those are really have the high skill, meaning that there are millions or even hundreds of millions of devices at some day you have to manage. This is really a huge challenging problems which you have to make decisions under uncertainties. It's really a decision making under a lot of uncertainties. How are you going to manage those from the security and reliability perspective? From the uncertainty perspective, I want to show one example here. Even from the renewable prediction perspective, you see from the prediction, certainly since this weather dependent, you are going to have uncertainties associated with your forecast. And this is a short term. If you look at 2 weeks later, the uncertainty may be even higher. For example, I worked with ISO. They told us if you forecast 2 weeks ahead for line maintenance, it may subject to 40% or 50% uncertainties from the forecasting perspective. That's huge. You have to really carefully evaluate the impacts from the grid perspective. So for that, you see, this is from the resource perspective, even from the physical model perspective. For those inverter-based resources, they are black box model, and some of the parameters, they may not be accurate. Meaning that if you rely on model for simulation, as we used to do, you can have a lot of inaccuracies in your simulations. And of course, one straightforward way is that if you have Fourier distributions, and then you just have a Monte Carlo simulation, you sample the space, and you propagate through nonlinear models, you evaluate the variable of interest, right? That's something you can do very straightforward. But the thing that we're talking about operational planning, meaning that every 5 minutes, every 15 minutes, we're also look at large-scale systems. Monte Carlo certainly is not the tool for us to get everything done within such a short term. So you have to come up with some more advanced approaches that can help you better predict the risks for the systems, and then put those risks into the mitigation schemes so that we can make sure our system is still safe and secure. And for that, a lot of people are trying to use machine learning and AI, right? But here, I want to give you some caution that although we have been seeing a lot of data growing in power and energy field, some of the data are even out beyond the power and energy field, like weather, off-domain, traffic data, gas usage, market data, water usage data. All those data are across different domains. You can say, hey, I have a lot of data. Let's try machine learning to address some of the problems. That's fine. We're coming this type of technologies, but remember, we are addressing our critical infrastructure with safety and security as the first priority. Mean that some of these approaches, you have to make sure you follow the physical constraints. There are limits. You must satisfy. You cannot go above. And also, we are not producing as much high-quality data as you are expecting in power and energy field. For some of the machine learning field, you have plenty of data, right? You can train a good machine learning model. But in power and energy field, we are certainly lack of high-quality data. For example, if you are dealing with stability, we don't have much disturbances in the field. We are going to train a model that can give you very reliable outputs, right? And also, when you are designing the machine learning approaches, they have to be adaptive and robust to different type of operational challenges, like the topology might be changing for the graph. And some of the data, they may be compromised, or they may be attacked by a cyber attack, right? And so on. So you have to make sure those approaches, they have sufficient robustness to handle. So given all those challenges, you can put everything into this big picture, which is the cyber physical energy systems. You see, you have the model responses, which you rely on the model. You can simulate whatever you want. And then in the meanwhile, you have measurements captured. It's very interesting. In the past, the power system planner or engineers, they use extensively model evaluations to come up with those risk assessment, design and mitigations, and so on, right? This is what has been done in the past. But nowadays, we see a lot of data or measured outputs from the sensors. So we're kind of shifting to another paradigm. Our model is not that reliable as in the past, while we're having growing data in our field. So the paradigm is that how you're going to better merge the data together with the model you have and come up with more clever decisions. And of course, this is also a decision making on the uncertainty problems. But you can kind of capture everything into this general framework. And that's what we are trying to do within our groups. For example, we're trying to develop some of the nonlinear dynamic estimation approaches to merge the data with the model, monitoring what's going on real time from the systems. On the other hand, we're trying to use the power of machine learning together with the physical information for risk assessment, optimization and control. And also, we're also trying to make sure you can use some of the physical information together with a sensor to help you better identify those cyber attacks. And due to the time limitation today, I will only focus on the second mechanism or the framework we have been doing. Is really how we're going to use the AI together with the data, physical information, to come up with better decisions. And for that, I will specifically focus on how we are going to embed the data and machine learning information into the optimization and control problems, where I'm going to show it in a more general manner so that you guys understand really the theoretical development we have been done, but those frameworks can be very general and they can be applied to many other domains. So to begin with, I would like to provide, first of all, a little bit of background about the optimization and control here. For example, if this is a constraint optimization problems, the first approach for machine learning applications that can you solve that problem many times, like using nonlinear programming or linear programming, and then you have those label data. You train supervised learning with the mapping relationship determined. Next time when you have new operation points coming, you just input into your trained neural networks, right? Give it a decision point. That's a very straightforward way. People have tried that, but again, our system is dynamic and changing. And every time when there are unexpected topology or reconfigurations, you have to retrain your model. And you cannot guarantee how the model is adaptive to different operation conditions. So that's really a drawbacks we have been seeing for direct supervised learning approaches for optimization and control. The other way that people are trying to see, can we formulate some of the optimization control problem into the reinforcement learning or dynamical programming problems, where you can formalize a state space, action space, following the Markov property, and then you explore the space so that you can make the decision and identify the control and dispatch strategies. For example, some of the ACOPF problems or preventive control problems, they can be formulated as a Markov decision process, and they use different type of deep reinforcement learning algorithm to solve that. Those are some of the approaches tried in our field. But again, for the DRL, you need a lot of data with labels, or even without labels. But you certainly you need a lot of high quality data. And some people may use the digital twins to generate additional data. But again, our model, as I mentioned before, the challenge is that the model is more and more challenging to model it in an accurate manner. So that's really the challenge we have to address, right? You tried supervised learning, you tried DRL, and so on. But still, there are a lot of challenges we have to address. That's where we come up with this physically informed learning for operation and control. So the key idea here is that you see, if you look at general, later I'm going to present the general optimization problems. And for those general problems, there are always some constraints that makes the problem itself non-convex or very difficult to solve. So the other idea is that can we use some of the data analytics or machine learning to replace those very difficult to solve constraints into a more easily way so that you can solve it. And of course, it depends how you're going to design that surrogate model or machine learning modules, right? And later on, you are certainly introduce another problem. Originally is the physical constraints. Everything is white box. But now you are introducing a neural nets, which is black box. And the original optimization problem will be a hybrid white box and black box one. How you're going to solve this problem efficiently, right? That's something we have to think about. We have to explore that. So for this problem, we tried, first of all, very straightforward heuristic optimization. It doesn't matter you have black box model or white box. I just search the space heuristically and get some suboptimal solutions. This is the first way we just tried. The second way is that for those really black box model, can you derive some analytic information out of there? For example, if it's a nonlinear programming problems, if you can get the Jacobian and Hessian matrix out of that neural nets models, you can use the interior point optimization problems and embed it in a much better manner, right? It has some analytics there. That's good. We're happy about that. On the other hand, is that you can use those build the surrogate model. You can let it to interact with the deep reinforcement learning agent. It gives you more information as compared better to the original model because it's not accurate. This surrogate model embeds both the past history data with inaccurate physical model. Certainly, you can generate more scenarios for DRL. We tried that. It also works very nicely under certain conditions. But the last way we will be really pursuing that for some of those non-convex constraints, can you relax it with certain assumption to a convex one, so that you can get the problem nicely done and get the global solutions, at least for the new problems. And today I'm going to also show some of the problems here. The last step is that you see we are using machine learning to replace some constraints. But how you are going to make sure those replacement is safe and secure? You say, okay, my prediction can give you 99.5% accuracy. But what about 0.5%? Right? The engineers, they are always going to question you. What will be happening if that is really critical? So we have to come up with some solutions. Let's certify for the 0.5, which is safe, which is unknown. If it's safe, go ahead, it's fine. For the other part unknown, I'm going to use a more conservative way, making sure at least my system is safe. So that's something I also want to share from this certifying the surrogate model predictions perspective. Just make sure everything is safe because we are handling our safety critical energy systems here. So to begin with, you see this is a general setup. You don't need to really look at those equations here, but I just want to point out that this is a general optimization of control problems in power systems. So you have the objectives, either minimizing the generation cost or you want to reduce the load losses or customer without electricity, right? Or you want to reduce the curtailment for renewable. You want to have more renewable integrated in the systems. While in the meanwhile, you have to satisfy the operational securities, either static security like powerful constraints, or some of the operational constraints like upper lower bounds for some physical limitations, right? And the most critical or challenging one is the stability constraints. This guy is giving you another dimensional problem. It's differential algebraic equation governed. It's very time consuming. It's non-convex for sure. For that, for this very difficult to model part, we would actually come up with some learning-based surrogate models. That's something, if you remember, I just mentioned that really this guy is giving us a lot of trouble. While for other parts, people have, smart people, they have done a lot of works for convex relaxation, very nicely done. But once they come up with stability constraints, nobody has done any works there. It's so difficult. So we're trying to say, hey, can we use a surrogate model based on machine learning to replace this very time-consuming, very difficult to handle problems into another form so that we can solve it, right? So that's something we're trying. Now the problem becomes how you're going to come up with the surrogate model, right? How you're going to choose, how you're going to design, so that they can be later embedded here as the security constraint optimization and control problems. So this type of setup, I think, is general to any engineering systems. But we have certainly some constraints in power and field.
So that's a question.
Sure.
What is delta?
The delta is a roll triangle or some of the dynamic variables we are interested in using to derive the stabilities.
So generator.
The roll triangles like transient system stability. You have to run time domain simulation to get the trajectories and decide whether system is stable or not. That's where very challenging.
Yeah, maybe quick follow-up. Why is constraint so challenging? Can you tell us? I mean, I don't know much about power systems.
Yeah.
So why is constraint so challenging?
Yeah, because this one is governed by differential algebraic equations. First of all, the differential algebraic equation is nonlinear. You cannot get a convex relaxation on that. The second one is that for large-scale system, it's extremely time-consuming to run even a single contingency there. So if you solve this problem in an iterative manner, imagine you may get days of them just to get one single solution. Our system may be, just totally collapsed, right?
This is only ODE, right? Not PDE.
Yeah, ODE. And of course, you can embed PDE depending on which problem you are interested in, right? So if you look at the electrical mechanical waves, right, that's a PDE. You have to embed it here.
So those T have a different time scale, right?
Yeah,
those
different time
T
scale.
and this T is much faster.
Yeah, this is much faster. So it's really complicated problem. That's why we want to, reformulate this problem at the same time scale, and it's easier to handle and very time, computational efficient. That's really the key ideas we're bringing. So the first try we're doing that. You see, let's look at that stability constraint, right? So as I mentioned, it's governed by the differential algebraic equations here, and X is the dynamic variables, Y is the algebraic variables like voltage, magnitude, and angle. And use the inputs like control or other inputs you have. And sigma here, epsilon here is some of the uncertainties. For example, unexpected outages, unexpected parameters, or some of the uncertainties associated with the loads or the inverter-based resources, whatever, right? So our idea here is that if you have uncertainties in the differential algebraic equations, how you are going to quantify that and reflect it in the stability indexes, right? And this process is very time-consuming to solve. And the first approach we tried is that can we use some of the machine learning approaches to really replace this very time-consuming process? And this process needs to be scalable, meaning that it must handle large-scale systems. So the first approach we have tried is Gaussian process, because it naturally gives you a confidence interval or probabilities associated with your outputs. But we understand that this approach is not scalable. And you can also use the polynomial calculus expansions, another analytical way to solve it. It cannot handle high dimension cases. So motivated by that, can we merge some of the information from the physics, like topology, some of the contingencies, embedded into the sparse Gaussian process? So I would like to mention a little bit about the comparison between Gaussian process as well as the sparse Gaussian process. A very quick recap. So for Gaussian process, you see, we're essentially trying to learn the the functional distribution for the outputs. So here, for this Gaussian process, you see the computational capacity is n power 3. N is the dimension of the variables of interest. Well, if you are using sparse Gaussian process, for example, for the Gaussian process, you don't need a lot of data to get their mean and variance. Right? If you have those two, the function is determined. So can we use some of the other variables, like similar to that posterior distribution, like pseudo data, M pseudo data, but they can approximately well for eventually the final Gaussian distribution you are looking for. So this is something the machine learning community have done. They use vibrational inference to infer the probability distribution or approximate the distribution for the Gaussian. And it turned out they can reduce the complexity into just linearly with the original number of unknown variables or interest variables you are interested. But M here is the inducing point. This is much less as compared to the original variable of interest. So you significantly reduce the computational complexity. And actually, it turns out this is really the case. For example, we use the Texas transmission systems. Currently, we're using 2,000 bus systems. And as you can see here, we compare with Monte Carlo. May take you definitely more than here more than an hour to get it done, or half an hour, because we are looking at here every 5 minutes or 15 minutes. You have to get all those risks down at that moment. And in fact, it can be found that using the physics info sparse Gaussian process, 900 seconds is close to 5 minutes, which is good. And you can further improve that using a more computational efficient computers. You can get it done. Actually, later on, we even make this approach more powerful to handle isolating the systems, 20K systems. We can get it done within 15 minutes. So that gives sufficient room for the operator to say, hey, within 15 minutes, I observe some stability. For example, here, this is stability indexes. If it's less than 0, that system is insecure. If everything is above 0, it's secure. And this probability distribution gives you a nice indication. Okay, how much probability I'm going to have troubles. So you can control this part so that you can still have a stable system. So this is the first. We come up with a surrogate model that is scalable and handle the risks induced by those uncertain parameters.
So what are you estimating? What is the accuracy? What is the problem is solved here?
So it's the transient system stability indexes. So I'm going to get the the predicted or calculated transient system stability indexes here, which is
so
here.
The goal is to estimate the transient stability index.
Yeah, it's this one. I'm going to make sure this one is done very fast, and it's quite accurate. But again, you cannot guarantee 100% accuracy. You can say, okay, 99.5.
So does it involve optimization or does
not yet, because we are trying to come up with some surrogate model just to first get this part done, and then we are going to talk about when you embed this part into the original optimization problem, how you're going to do it. Right? We go step by step from here. So this is the first we have done, directly getting the mapping relationship with inputs to the system stability indexes, which is good. I think I'm happy about that. But this framework is not general enough, meaning that you can only evaluate certain scenarios. But the other problem we are looking at is that can you get the direct prediction of the system dynamics with all the state variables predicted? With that, you can calculate all the stability indexes you are interested in, right? That would be more fantastic way. So we kind of formulated the problem as, give me some of the inputs, measurements. Can we input those disturbance data into the surrogate model? I can give you the trajectories for all state variables. And from the state variables, you can calculate whatever you want with different type of constraints. So for that, we are further improve the sparse Gaussian process here. For example, it's an extremely high dimension here. The first one is that we want to reduce the state space, right? The feature space. So we use the deep kernel approaches to extract the key features in the latent space, which is reduce a very small dimension. That small dimension can be effectively taken by the Gaussian process, less than done. I think that gives us the power to make it sure that this approach can handle very large scale space. I think we use these approaches certainly for thousands and tens of thousands of systems by using such a way, to better manage the significant outputs of a number of outputs, and as well as the high dimension from the state projection perspective.
What is the input here?
The input is a PMU measurement, like capture the frequency, voltage, real and reactive power measurement captured by PMU measurements. When there's a disturbance happening on real time, you give me the inputs within within seconds, 1 second, of course. You can predict the trajectory for the dynamics, whether the system is stable or not. I will show here. For example, we're going to have a discriminator to see whether the system is okay. All the oscillation can be damped out, which is good. I'm not worried about it. But if you predict any of the out of steps, mean that the system is unstable, you have to take immediate actions. That's where the time matters. Within a couple of seconds, you have to get the control actions done. Otherwise, the system may be collapsed. So this is really a strong motivation. You have to have a very efficient surrogate model to give you that type of information. And we tested in the system. Here you see on the left-hand side, again, since it's a Gaussian distribution, you still have nicely confidence intervals associated with that, right? You can have the confidence interval for the predictions. For the unstable cases, we can also clearly indicate, okay, the system within a couple of seconds is going to be, like out of step, meaning that system is going to be unstable. So you give that information within, milliseconds. Actually, at least comparable with the PMU sampling rate, which is good. You have the time to do emergent controls to maintain the system stability. So up to that point, I mentioned about, couple of approaches. Of course, I just listed 2 examples. How we're going to come up with, computational efficient surrogate models to replace this very time-consuming part. And also, you are going to have like a matrix type of operation black box model here, right? Now, let's look at this problem, optimization. You have the stability constraints down nicely and reduce the very compact form here, replace this part. But still, this is an optimization problem you have to address. And it's a black box model. Again, the first approach we tried is that, can we just use a heuristic optimization? There are many different versions, right? The advantage here is that even you are using the heuristic optimization, because due to the neural network's surrogate model, every evaluation is so fast as compared to the time domain simulation here. So at least the only benefits I can get is accelerating the optimization problem itself here. So we tried, just use heuristic optimization approaches and input into that preventive control approaches. We can see, it's good. It's conservative, but it gave you the control of the system into a stable status.
Yeah, I guess if you could go back to the constraint, I'm
Yes.
trying to understand. So if you surrogate replace the left-hand side, how would you guarantee the constraint, satisfaction in that case?
Yeah, so here you can reserve a little bit margin. You can relax the margin, safety margin a little bit more.
So
make it more conservative.
Or something.
Yeah, you make it more conservative here.
But would that be an issue? Because basically the Gaussian process is infinite horizon. Would that be an issue if the constraints be violated?
Yeah, sure. I think later on we're going to elaborate how we're going to improve this process, because we tried first step, right? We want to see whether it works or not. So at least here we find out, okay, it gave you the benefits as we are expecting, accelerating. The first benefits we see it. The other one is that I'm not happy about heuristic optimization. I don't have any guarantees there.
Right.
So but if you look at the problem itself, it's still like an optimization problem you see here. I'm still having a surrogate model there. It's represented by deep learning, right? So the optimization problem, you see other constraints I can easily handle with the existing development. The only challenge is about this. If you can derive analytically the Jacobian Hessian of these constraints, you can use interior point optimization to solve it, right? That's the objective we're trying to solve, you see here. So can we derive the Jacobian Hessian for this black box model, right? That's the question we want to answer.
Can I quickly go back? So for the estimation of Gaussian process estimation, surrogate model, how is it differ from things like dynamic gradient? Gradient means there's a method of gradient, in this case the Gaussian process for surrogate.
Yeah.
And they have this dynamic version, which seems similar to what has been done here. Did you ever do that?
Yeah, I think for this part, we give 2 examples, right? We give 2 examples, but the approach is how you're going to formulate the surrogate model is depending on your problem setup. So it's quite broad, but we want to bring the idea that certainly you can have a surrogate model here to help you. You can choose different machine learning approaches, whatever, depending on your problem setup. So again, back to the problem is that if you can get the Hessian and Jacobian from this problem, original problem, you can solve it in the interior point optimization. Can we really do it? Yes, of course, depending on the structure of the deep neural. So here, if this is like using certain activation functions, like renew functions, you can derive nicely that you can do the forward propagation. You can derive analytically the Jacobian matrix for the deep neural networks. You can also derive the Hessian matrix back and forth. Then you can have the second order here. It's analytically done, which is great. I have the analytical Jacobian and Hessian matrix. So my whole problem, I can solve it into by using interior optimization problems. It has certain analytics there. I'm very happy, right? It's much better as compared to the heuristic optimization. So this is the first. So we apply this type of framework to the look ahead preventive control. Like every 15 minutes, I have to make sure, based on the forecast as well as the system constraints and stabilities, can we have some of the critical passes here to make sure it is stable. For example, here under certain scenarios, the system is unstable. For example, M1, MS, M1, MS, and M1. If you don't get this properly done, you'll have the system unstable. Certainly, we want to replace and improve that process. And by using the framework I just mentioned before, here you see we can use this preventive control approaches to dispatch the event generations, the battery, and synchronous generators to reduce the risk of the system. For example, eventually make sure the system is stable. And one very interesting finding we got from the derivation is that you see we have Jacobian. Normally, Jacobian is related to the first derivative, right? And that is related to the sensitivity indexes. So I mean that I can look at the system stability margin and look at the sensitivity between inputs to the margin. I can see some of the variables, they are very sensitive to the stability margin. And those factors, they are very essential. So I can control those essential variables to come up with a solution. That's really some surprise to our development. So you can purely rely on the sensitivity to come up with the decisions to mitigate the risk of the systems. So this is something very interesting, going beyond our original design, but we find it very useful. So we advanced a little bit step. Okay, we have a little bit more analytics, right? So, but because that prediction is still like if you are using deep neural networks, it's a deterministic stochastic. Meaning that you give me the prediction, there's no uncertainty, no risk associated with that. I want to improve that process, right? So later we try another approaches, which is using deep neural networks together with Gaussian process. Because using Gaussian process, the beauty is that you still have that uncertainty quantification, and also the Gaussian process is an analytical Gaussian distribution there at the end. So you can kind of, for the normal distribution, you can convert the chance constraints into an analytical form. So that, for example, if this is a probability constraint, right, it's nonlinear, normally it's non-convex, you cannot solve it. But using analytical way of transforming it into a deterministic form, so the Gaussian property. And this is an analytical one. The original problem, the chance constraint problem, is now confirmed into a deterministic optimization with analytical solution here. And also you have the risk quantified much better as compared to the original DN approaches. And also for the Gaussian process, you can certainly analytically derive the Jacobian Hessian. Much better job, or much better advanced as compared to DN approaches, right? So we tested. We found out from the TSI or transient system stability index perspective, we can quantify the risks for that stability margin prediction. And we embed this prediction into the decision-making process, chance constraint optimization. You see, originally you have system stability issues, but after control, everybody is back to normal. I think it's desirable, right? Which is great. We love it very much, but still, you have certainly some assumptions here. The system stability index, they must be, well captured by the Gaussian distribution or Gaussian process, right? But what happens if they are not? And also, since there's still a nonlinear optimization problems. You may have convergence issues, right? So the question we are asking ourselves is that, can we make the constraints into the very particular form where my control variables and system stability indexes, they are convex with each other. I don't necessarily getting the whole surrogate model to be convex, but I'm interested in if my control inputs are convex to the control variables or the stability I'm interested in. And then, because I'm interested in control them, make sure the optimization problem they are converged, right? So that's something we find there's some advancement in input convex neural networks, which means that originally it was designed to make sure all the outputs of the ICN is convex to the inputs. But this one is at huge price, the cost. I mean that you have to train this model. It's very difficult to converge for large scale systems, very complicated problems. So we come up with a better version. Can we just make sure the structure is partially convex, meaning that some of the inputs I want to control, they are convex to the outputs. Well, for others, I don't care. I don't want to control them, right? So we design in a particular manner and make sure our control variables, they are convex to the system stability indexes. And then we put this surrogate model into the original, like ACOPF. And ACOPF can be relaxed, convex relaxation. So the whole problem now is convex. So I can solve it. So we tested here. Actually the results are under this paper, but due to the time, I'm not going to elaborate. But certainly we get all the converged results. So it's 100% guaranteed to converge. And you can certainly put some of the constraints there to make it a little bit more conservative, but at least they'll give you 100% converged results there. And it has not been fully done yet. You know why? Because for those ICN or PICN, they cannot give you 100% accuracy for the surrogate modeling. As I mentioned, you can give 99.9% accuracy. What about 0.1%? If that's an extreme event, you cannot work, right? So the engineers are very cautious or conservative about that. So the approach we're doing is that, can we certify those outputs, the surrogate model outputs, right? If I can, from the theoretical perspective, I can certify, oh, this is really give you the accurate results, fine, I can go ahead. While if it's not, securely certified, I'm not going to use the this type of approaches. I'm going to switch to a really conservative way, making sure our system is stable. So there are some advancements in the certificate of the neural network outputs. For example, the first one is the linear programming verifier, meaning that for the activation function, because really it is the activation function that gives you a nonlinearity in a neural networks, if you really look at those neural network design. Otherwise, there will be matrix linear modification and so on, right? Or linear combination. But it's really the activation function they are giving you a nonlinearity. So we can use the linear programming to relax non-convex renew constraints into a problem into a linear programming one, so that I can verify, for example, which it's even at the 0, 1, or the saturated one, or a linear relationship. You can certify from the theoretical perspective, right? And based on that, you see, okay, if I can certify my prediction is right, then go ahead, no problem. If not, I switch to another approaches. And there are also other advancements like alpha, beta, cron. This is done by mathematicians. They can do a more like tight bound for the certification. For example, here for the alpha, cron approaches, they can back and forth using a gradient ascent approaches to optimize the lower bound, so that they can tie the lower bound to make sure it's more secure, really in a good manner, quantifying and certifying the constraints. Also for beta cron, they combine branch and bound approaches with Lagrangian relaxations to certify the neural split constraints. But the whole point here is to make sure the neural outputs, their outputs can be certified. Either is correct, or unsafe, or unknown. I don't know. I cannot certify. So for that, you have to switch to a conservative manner, right? So this is the whole framework you see here. From the beginning, I have this stability estimation or Jacobian Hessian calculated, right, as we have done before. Now let's certify whether those predictions they are safe or not. So we go through the alpha beta certification process, and if we identify that the system is unsafe, okay, let's switch to a conservative way. Let's control the system. If the system is certified that the surrogate model is right, then just go ahead and perform the controls. So that's the basic idea here. So you see, we tested in a system in the North Carolina systems. As you can see, for the perturbation here, I can certify there are for some samples. Some of the samples they are unsafe. Some of the samples are safe. So I can tell you, the maximum possible perturbations you can have, out of distribution perturbations you can have, making sure I can still certify the surrogate model accuracy. So based on this certification, I'm going to take actions to control that. So for example, here, you see at the beginning I certify, oh, this is unsafe. I have to iterate, find another policy, and certify iteration. And after 2 consecutive certification, I find, oh, this is safe. You see this stability indexes is great. So this part is done. So mean that now I don't have the risk that you are questioning even the surrogate model is not accurate. But I can still certify. I know that this prediction is not accurate. So I can switch to a more conservative way for doing the job. I don't think we have the time to go through this, but just a very high level mentioning that you see in the original, this AC or security constraint problems, we formulated in an open problem, right? But the other way that you can use the surrogate model, interact with a deep reinforcement learning agent. It's not like through everything analytically. For very complicated problems, you can use this surrogate model. For example, for distribution systems, it's very difficult to model it accurately. So you can use some of the models, like as well as the history data, to come up with a surrogate model. You net the surrogate model to interact with the DR agent and train the policy so that you can make optimal decision makings. For that surrogate model, it's designed particularly for these systems, is that you have lots of low quality data, lots of them. You have very few high quality data. So the question we are trying to address is that can you use massive low quality data together with a few high quality data to come up with a converged solution? It gives you still reasonable predictions. That's something we are trying to do, right? So the approach we use are multi-fidelity neural networks approaches. The high fidelity, the low fidelity data is to give you a trend. So they give you a trend, how likely it's going to look like. While for the high quality data, we're going to fine tune those trends so that at the end, we can still achieve a high fidelity prediction. So the example here I'm showing that if you have enough high quality data, 100K, this is the accuracy level, 10 power minus 4. If you have enough low fidelity data, same level is 2 orders of differences. If you have limit high fidelity 1000, which is 10 power 2, still no big improvement. But if you have 1K plus 100,000 low fidelity, you're achieving similar level as the high fidelity data, which is great, which would be really similar to the actual scenarios we have been seeing in the field. So we train and get this multi-fidelity learning-based surrogate models, and then we interact with the deep reinforcement learning agent. For example, we use these actual systems. From Colorado, this is an actual utilities feeder with lots of solar integrated. The objective here is that I want to control the solar spine inverters so that I can regulate the voltage into a safety margin while minimizing the curtailment for the PVs. Right? I don't want to lose of a lot of PV generations. So that's the objective. So we kind of here categorize the system into the deep reinforcement learning problems. The inputs, observations are low shapes, how look likely the PV generation look like, the maximum value of the PV output, real active power, and then the actions that how you're going to determine the setting point for the PVs. The reward, as I mentioned, is that to minimize any voltage violations in the systems while minimizing the PV curtailment. So those are the rewards. So we train the agent and we compare, actually we're testing that actual system with data. We found that even with those multi-fidelity learning, we can achieve quite similar level with the model where everything is perfect, you have full observability, all the information you have, we can achieve similar level. I think this is very interesting results we got out of that practice. We're still improving this process, and I think by next year we're going to implement this in the field. Working with great edge control companies, we're going to test it in the field and see how we're going to dispatch the PVs and batteries together for managing the demand response, the voltage regulation, and so on. As a summary, we find that learning a surrogate model to replace very complicated to handle constraints or reducing the complexity, they can accelerate the computation process, as we showed many problems or examples. The other way is that physical-based approaches, they can help you better design the solutions that can fit into your engineering problems. But there are certainly some of the gaps we have to address, as I mentioned before. You have to carefully design the surrogate model with physical informations for different applications. This design is different. The other one is that we have to make sure those surrogate models, they have sufficient robustness to the data quantity issues, right? We haven't considered that data quantity issue yet here in our current development. So we are working to improve that process. We are also trying to develop some of the approaches handling out of sample distributions, like unexpected changing to the system operation condition and so on. So this is still work ongoing. With that, I want to conclude here and open any questions you guys have. Thank you, guys.
Thank you very much. Guess we can take a couple quick questions.
Yeah, feel free to ask. I hope this framework I put it in a way that is not really Parsons hardcore, which you have no clue. Some of you guys may not coming from the Parsons background, but this is like really a OR problem or optimization problem, but how we're going to go step by step to solve it.
Maybe I could ask one. So
Sure.
maybe better optimization of the differential equations. How would you guarantee the quality of the solution in the end? Because this is really about local optimum. You mentioned global optimization, conversation.
Yep.
But fundamentally, it's a local optimum, just like the same way we train the deep learning models. One local optimum versus another local optimum. So how did you guys look at these problems?
Yeah, you see, our last approach we recommend is the one we have the convex form. At least for that particular, relaxed one, you are having global optimal for that, relaxed problem.
Yes.
At least it's a good enough suboptimal. For power engineering application, you don't really need to get the real global optimal. As long as those local suboptimal solutions, they are close, they are not too far away, which I think from the initialization perspective, normally if you design carefully with engineering knowledges, you are not really far away from that. It's good enough for practical application.
Mm-hmm.
Yeah.
And maybe the other quick question is, there are a lot of interest right now about deep learning, generative AI.
Yep.
And of course, I understand in your case it's mobile, with patient-based, theoretical guarantee, machine learning measures. But do you see the opportunity to use some of the, very much black box models in this context? Or do you think it's better to still stick with the clear understanding, kernel-based statistical machine learning measures? That's, there's really a lot of debates right now in terms of these two domains.
Yeah, and I think for generative AI, there are a lot of potentials in power energy field. Because our group, we tried a couple of them. For example, we use the large language model to help us detect cyber attacks, because you can input human information. It's not like digital data you capture in the field, but you can have human information like text or knowledge into that. The beauty for the generative AI or ChatGPT is that you can always provide human inputs, experts input. Yeah. We find that's extremely valuable for our systems. Because there are certainly many experienced engineers. They have a lot of knowledge. They are not reflecting any of the data showed in the field. But if you input and get trained, or you let them chat, right, correct their behaviors, certainly you are going to have a lot of applications. One straightforward application that for the system operators, they have a lot of rules, manuals, and those are documented. So you can train a large language model and put all the documents to the large language model, and then you ask them the rule, and they can even quickly give it to you. Right? You don't need to rest through the documents and get those things. Very straightforward. The other thing that for some of the data lacking errors, you can use the generative AI combined with physics to generate sufficient data for other applications, right? So certainly there are lots of potentials for the generative AI, and in our field, we are exploring. Many people, they are starting to explore and identify the critical application scenarios and so on.
Well, I guess we are running out of time, so any last minute question? If not, let's thank Professor Zhao again for the question asked.